next paper is entitled Influence of Low Dynamic Response on the Stability of Microgrids During Islanded Transition. And it will be presented by Juan Diego Rios. We have been asked just to use the video.
Yes, please, Mr. Chairman.
Okay.
Thank you.
I'll do my best.
Thank you.
Let me just okay, so let me just to share my screen. Okay. Okay, so do you see my screen?
Yes.
Okay. Okay, let me. Okay, sorry. Let me. Okay. Okay.
Good afternoon, everyone. My name is Juan Diego Rios Penaloza. I'm a PhD student in the University of Bologna, and I'm presenting the paper entitled Influence of Low Dynamic Response on the Stability of Microgrids During Islanding Transition. The authors of this paper are myself, James Sadu, Alberto Borghetti, Fabio Napolitano, Fabio Tossani, and Carlo Alberto Nucci, everyone with the University of Bologna. The motivation of this paper, according to some recent surveys, loads are often represented using static models in dynamic power system analysis, performed usually by transmission and distribution system operators. Even if the importance of accurate load modeling is widely acknowledged, an indication exists on the important role of load dynamics. This paper aims at exploring this issue concerning microgrids, for which the influence of the low dynamic response might be very important. Indeed, the results of a previous work we carried out show that during an islanding transition in which all resources are controlled in the grid following mode with the group control strategy, the stability is granted only for a large amount of rotating load. Such influence has been exploited, for example, in some control strategies in which the voltage of the distributed resources is controlled in order to modify the power consumption of the load. During unplanned islanding transition, as the voltage will fluctuate, also the load consumption will vary even without applying any intentional control. For microgrids, particularly for those characterized by the absence of rotating generators, load dynamics considerably will affect its transient stability performance. So, the aim of this paper is to assess the influence of load modeling and composition in the stability analysis of a medium voltage microgrid during unplanned islanding transition. On one side, we analyze the influence of load modeling by considering typical load models used by system operators. On the other hand, we analyze the influence of load composition by carrying out a sensitivity analysis first, in which we study the impact of some load parameters. And this analysis is then extended to a more complex grid in order to assess the impact of different load classes we considered in this case. Okay, for the first analysis, we define first of all the static load models. We use the exponential and the steep load models, which are very popular among utility operators. And then we also consider constant impedance and constant power type of loads, which are just a particular expression of the previous load models of the exponential and of the steep models. Concerning the rotating loads, we consider two different models of the induction motors. First, we consider the full model implemented on the EMTP software, which is in practice a fifth order model of the induction motor. we consider also a simplified model, which is known as a sleep model, which accounts just for mechanical traction. Concerning the load composition, we consider four different types of loads: residential, commercial, industrial, and agricultural. Here you can see the load composition we consider for each class, so the percentage of each load component on each load class. This is a study system in which comprises a synchronous generator, a PV power station, and two battery energy storage systems. Loads are connected to all buses, but the composition of each load in each bus is different.
Oops. Oops. I'm sorry. I don't know what has happened. I'm sorry. I don't know what has happened with the video. Let me just try again.
Good afternoon, everyone. My name is Juan Rios Penaloza. I'm a PhD student in the University of Bologna, and I'm presenting the paper entitled
Let me just to share. Oops. Okay. We were here. We were here. Okay. Okay.
storage systems. Loads are connected to all buses, but the composition of each load in each bus is different.
Oops. I don't know what has happened with the video.
I can share the video, I think.
Can you?
Yeah,
just
I'll try.
Yeah, thank you.
check that your version is better than mine? Okay. Are you sharing?
Each load in each bus is different from the other ones. Also a circuit breaker, of course, which couples the microgrid to an external network. Here we reported the parameters of the synchronous generator and the PV power plant. And here we describe the battery. Both batteries are controlled in the grid following mode with a droop control strategy in which the active power responds to changes in the frequency and the reactive power responds to changes in the voltage. The control system is depicted here. A PLL gives the angle for the park transformation and anti-transformations. And here you can see the contribution of both groups. Then a current reference control in cascade with a voltage reference control. The parameter of the base are reported here. We consider two 1 megavolt ampere storage systems in which the active power droop is considered to be equal to 2.4% and the reactive power droop is 10%. So we can start describing the first analysis, which is the assessment of the influence of the load modeling. 6 cases were considered. In each case, stationary and rotating loads are modeled in a specific way. For example, in the first case, rotating loads are represented by the EMTP model and stationary loads are represented by the exponential model. We retain that this model is our benchmark since it is the more detailed one. For the other cases, we consider a slip model for rotating loads, for example, and exponential or a SIP model for the stationary loads. In the last three cases, also rotating loads are modeled through a static model. It can be the exponential, the constant impedance, and the constant power model. So two scenarios were considered, one in which the synchronous generator is connected to the microgrid, and one in which it is disconnected. A three-phase fault is simulated at some point, and 15 milliseconds after, the circuit breaker opens, initiating the islanding transition. Here we can see the results for the frequency and the voltage for all the models, except for the constant power model, which represents an unstable response. In all figures, the benchmark was reported. You can see that some differences are present, but the overall influence is not great in this case. For the second case, in which the synchronous generator is disconnected, only models which include the rotating nature of the loads represent the stable transient response of the microgrid. So the EMTP plus exponential model, the slip plus exponential or SIP model. This is the first main conclusion we arrived. Okay, the second analysis studies the influence of the load composition. First of all, we carried out a sensitivity analysis, as I already said at the beginning of this presentation, considering a simple system with just one battery and a combination of rotating and stationary loads. In this case, the fault is not simulated, and the circuit breaker is supposed to open, initiating the islanding transition. The load is represented by our considered benchmark, so I'm referring to the EMTP model plus exponential model, and the base values for the loads are these. We start varying them one by one and see what happens. In this slide, we report the influence of the inertia constant of induction motors and the influence of the percentage of rotating load. The increase of both, as you can see, leads to a minor frequency and voltage deviation. In this slide, we report the influence of the exponential parameters related to the voltage, as you can see. The increase of the active power parameter, KPU, leads to a minor frequency and voltage deviation, while the reactive power parameter, so KQ, leads to a greater frequency deviation but a minor voltage deviation. In this slide, we report the influence of the exponential parameters related to the frequency. As you can see, the increase of the active power parameter leads to a minor frequency deviation, not having any influence on the voltage. And the increase of the reactive power parameter leads to a minor voltage deviation but a greater frequency deviation. Finally, we analyze again the complex network, which is a Segre benchmark model. As you can see in this analysis, the synchronous generator is disconnected from the microgrid. As I said before, we consider the load at each bus to have different load compositions. Practically different percentage of residential, commercial, industrial, and agricultural loads. In order to compare the results to some of the results obtained with the sensitivity analysis, which is our guide, we defined some equivalent parameters for all loads in the network. The equivalent inertia, which is related to the portion, just the portion of rotating load. The equivalent parameters for the stationary loads, which are obtained through a fitting process. And finally, the equivalent inertia of the whole system, okay? So this last parameter is related not just to the portion of rotating load, but to the entire system, to the entire load of the system. Okay, so we analyzed 8 cases in which we vary the percentage of the load classes at each bus. Then we calculated the equivalent parameters for all cases. As you can see in the first 4 cases, the inertia, the percentage of the rotating load, and KPU increase. The other parameters vary very little, so it's difficult to consider them. All in all, we can expect an overall increase of the frequency and the voltage. For the last 4 cases, it's more difficult to say what is going to happen since the variation of the parameters is less monotonous. Particularly in this case, we are going to lean on the expression for the inertia of the whole system. We can see the minimum frequency for the first 4 cases. It increases as we expected, and also for the last 4 cases. Notice that in the x-axis, we have the inertia of the system and not of the rotating loads, of just the rotating loads. The voltage also increases for the first 4 cases with respect to the system inertia, as we again expected. But for the last 4 cases, increases except for case E, in which we can arrive to this conclusion that some of the other parameters might become more influent. So we arrive to the conclusions. The paper has analyzed the influence of load modeling and composition on the transient stability of a medium voltage microgrid during islanding transitions. Regarding the influence of load modeling, 5 case models were compared to a reference model which was considered as a benchmark. If the synchronous generator is connected to the microgrid, which is the only distributed energy resource with rotating inertia, all models except for the constant power model predict the stability of the microgrid after islanding. If the synchronous generator instead is not connected to the microgrid, only the models that include the rotating nature of the loads represent a stable transient response of the microgrid. Regarding the load composition, the increase of the inertia constant of induction motors, KPU, and the percentage of rotating load improves the power quality during the islanding maneuver in terms of minimum frequency and voltage variations. The increase of KTU instead worsens the voltage profile but improves the frequency nadir. For the case of the Sigre benchmark system, which was the complex network we analyzed, they consider industrial and agricultural classes of load are more prone to easy the islanding transition with respect to the residential and commercial classes. This is because of the larger values of equivalent inertia and the percentage of rotating load. Here I reported the reference we used to write the paper, and I thank you all for listening to my presentation.
Okay, Juan Diego, thank you very much for your presentation.
Thank you.
You have a couple of questions.
Yes. About the first question, I'm not really sure if it's directed to me because it's quite different to my work, I think. I mean, I didn't. The question is, can PMU measure the active reactive power, voltage, and frequency data by 1 millisecond? But yeah, I don't think it was related to my work.
Probably so, it's for the previous paper that arrived late.
Okay.
I would appreciate if the author of the previous paper can answer this question. So please go ahead.
Yes. The second question is, did you consider load and distributed energy resources under overvoltage and under overfrequency tripping in your analysis? This might have a significant impact on the islanding transient behavior. So yeah, this is a really good more, I consider it more a comment than a question. It's a really good comment for me. We did not consider the under over voltage nor the under over frequency tripping because we wanted to analyze how just the loads behave in the transient during the islanding transition. So if we wanted to, for example, consider also protection schemes, for example, we would certainly influence the overall transient behavior of the microgrid. Just adding to this comment, we are now, for example, making some sort of similar analysis in an already islanded microgrid with grid forming units. And for example, we are considering the fault current limiter, which is a characteristic of the power converter, and we see effectively that it has some influence on the transient behavior. In this study, we wanted just to analyze the load response, so we disregarded these protection schemes.
Okay, thank you very much. Thank you very much, Juan Diego.
Thank you. Thank you.
For your excellent presentation. Thank you.